Welcome to RPI Data Science. So last time we talked about regularized regressions. So in case you haven't watched that video, I do recommend watching it. It's part 20 of our text classification tutorial, and you can actually go to the playlist and you can check this video. And once you understand that, this would be a theoretical implementation, practical implementation, because we have seen the theory. Now we will see the coding. And first, we will start with ridge regression. And if you remember, we have said ridge regression is an extension of the ordinary least square regression, which is the objective function is to minimize the sum of square errors, and that is a ordinary least square regression. But to make it ridge, you add penalty term, and that penalty term is calculated by this additional formula. But if this is 0, that means your model is sum of square error. And we have really talked something about ridge regression in the past video. I do recommend watching it. So today I want to go further in that, and we will use GLMnet, and this is a package that I have already mentioned in my past video. It's a great package. It's very fast, and I heard from the author of the package that it was written in Fortran. That's why it's lightning fast, and it's actually one of the fastest algorithms that I have seen. This is GLMnet is one of the fastest, and quantitative text models, of course, it's also very fast. And probably XGBoost, this XGBoost package to do XGBoost algorithm, this extreme gradient boosting, that's also very fast algorithm. Otherwise, the other ones like SVM, it's really slow, and also the other ones like if you do KNN, for example, it's kind of lazy. It's actually called lazy learner because it's really slow. So they are very slow. So GLMnet, I do recommend also looking at the package and the functions within that package. This is really very long. If you are really interested in using this algorithm, then I do recommend looking at the functions and try to have a better understanding of the functions behind this package. And also you can actually not only with GLMnet, you can do other models like Poissons or something. Also Cox regression models. I personally haven't used it particularly, but there are a number of other packages other models that you can use this package for. So we have already done our text pre-processing using Quantida, and we have already developed our document feature matrix, and we have document feature matrix, TF-IDF version of our document feature matrix, and we have already seen that in the previous tutorials. And I will not go further in in the text pre-processing. I have already have pre-processed data. I will simply plug in that data into my model and see the model training and also the prediction and the like. And finally, we will do tuning cross-validated ridge regression model. So we'll do tenfold cross-validation model. We will not do like repeated cross-validation or something, but we'll just do tenfold cross-validation, and we'll see. And in between, we will also visualize the models, and then finally we'll do variable importance. So we will use the VIP package, and we will somehow see like 20 most important variables within the model. And then at the very end of our session, we will see evaluation of the models. And the models that we have, we will develop. We can evaluate it using the prediction. We will give it a test data, and we will see how it performs in predicting unseen data. Yeah, so let's get our hands dirty. So the first thing we need to do is we need to fit a ridge regression model. For that, we have to do is library, and we need to put our library GLMnet, and that's one of the libraries that we use for today. And the other one is a library. Another library we will use is VIP package. I don't use any other library, so I will simply work only with these ones. So once I load this, and let me just assign time, and the time would be, because I want to check how fast this model is. So I will use system time, and then from there I can simply call my model ridge. Let me call it ridge, and then GLMnet provides this function called GLMnet. And then the first thing you have to do is you need to give it your data, and our data is the train data. So the x and y variables. So the x is train df mat, if you remember from our previous tutorial. So df train mat, and the y variable is we need to give it a y train, and that's train include. Then after that, I will define that I'm doing ridge regression, which is defined by alpha equals 0. That means if you write alpha equals 0, that means you are telling your algorithm, you are telling the package, this GLMnet function, that I want to run ridge regression, not lasso or elastic net. And the other one is you need to define family. I'm sure you already know this one, because if you have already worked in ordinary least square regression, or maybe other regression methods like Poissons or logistic regression, you always have to define family. So for ordinary least square regression, you define a Gaussian. Here for logistic regression, you define binomial. So we are doing an extension of logistic regression. So we simply use this binomial term, and then after that we are done. So we simply finish this line, and then we calculate our time and see how long this process takes. So let me calculate my time. System time minus time then this will calculate how much or how long this takes. So I will again do for reach TF-IDF, and for that I simply will do the same process. This is not so I will call this one TF-IDF version of my data, and then I mean for this one I will change the data because I'm using the TF-IDF version of the data. Otherwise everything will stay the same. I'm using the TF-IDF version of the data, and then I call this TF-IDF, and then the other one I do the simple frequency version of the data. Now I have everything, and this is a simple not a cross-validated version of ridge regression, and then I can simply run this. This is lightning bolt fast. It's very fast, so it will take only very few seconds, not even 1 second. So the first one is taking 0.41, and if I give it the TF-IDF version of the data, it will take only 0.3 seconds, which is very quite fast. But if I give it the next one should be I will do cross-validation. So for that I will use CBGLM, but this is a quick. I will simply visualize it, and then I will show you how this model looks like. So the first thing to visualize this is I can also actually look at the summary of the model if you want. So you can see summary, just like every other model, every other regression model. You can see summary and summary reach. Oh, it's still running. Okay, I don't know. Yeah, it seems it's already finished. And let me run this. And this is how the model looks like. So if you see summary of the TF-IDF version of the data, so it will take like A0, alpha 0, 100. These are really the main values of the model. So lambda I have 100, and then the DF ratio and in the past. These are really I mean these are some of the values of the model. But you can see also like the values if you want. So you can simply reach TF-IDF and then call your whatever you want to see. For example, if you want to see the call, like call is will be how you call the model. Yeah, so this is how we coded our model. So you can also see the other ones like that, but I don't want to spend much time on this. And the next thing is I want to visualize it. So to visualize, you just simply use a bizarre plot function, and then the reach. So you simply use the reach, and then you define the x bar. So the x bar will be lambda, because lambda will be our x bar. And if we run this, we will see how our reach model looks like. Yeah, so this will be how this is how our ridge regression model looks like. So as you can see, this is the 0 coefficient, and then above 0 there are positive values, and below 0 there are negative values. So you see as lambda value, it's actually log lambda because it's logistic regression, and I mean it's the extension of logistic regression, logistic ridge regression. So as lambda value goes to infinity, this value of these coefficients they will be pushed towards 0. So if you see while around close to 1 or something, these coefficient values are high, very high, like 0 point something compared to somewhere close to 0. It starts from higher values, and then as lambda value goes to infinity, and this value starts getting to I mean these coefficients start approaching 0, but it's not all the way to 0. It doesn't touch 0. If you zoom out these pictures like somewhere very far, if you zoom them, then you will see this the variables, the coefficient of the variables will not really touch the model. So let me give it a title, and the title of that ridge model will be ridge. Let me call it just ridge, and see where that title appears. Yeah, now I have the title, but there is a little bit, it's touching the value, I mean the value, so I want to see a little space. For that I want to add something just around here, because I want to create a space, and for that you just make this sign, and you just give it one new line, and now it should be fine. And for the next one we can also already do it, and then for that, so now we already have a space. Actually we can also give it another one, but it's fine, I think it's okay. And the other one is reach TF-IDF, reach TF-IDF. So we have already reach TF-IDF, and now if I plot them, they will be plotted one after the other. So but I want to plot them side by side. For that what you can do is this par function, and then MFO. I think if you are into bizarre you know it. So 1, 2, so because I want to plot them in one row, but they will be in one, or both of them will be in one row. So the next graph should appear here. So let me run this and see how the plot looks like. And then we will see actually this one should be reach TF-IDF, sorry, reach TF-IDF. So I will need to rerun it again. Yeah, so there you go. I have my models, and it looks like this one is a bit like you see there's I mean it's somehow, because they are congested, I mean we need to somehow change. We can change them by changing Jupyter options, and you can have a better bigger picture of this plot. But if you plot them side by side, this is how they look like. But you can do better like looking like better visualization or something. But otherwise in those cases, you know, the model coefficients are pushed further to 0, but there are other models which are still having high coefficient compared to the one here. So the next one, moving on, what I want to do is I want to do cross-validation because this is a simple model, but I want to see cross-validation of this process. I want to do tenfold cross-validation and mark where my best model is, because this is just simply giving lambda values. It's doing many lambda values, 100 lambda values actually, but it's not doing tenfold cross-validation. It's simply tuning based on lambda values. And the GLEMINATE provides this 100 lambda values, but CVGLEMINATE gives tenfold cross-validation and then all these 100 lambda values for each sample of the data within this tenfold cross-validation. 9-fold of the data will be for the training, and 1-fold of the data will be for the testing. For that, I will simply call reach TF-IDF, no, reach cross-validation, and then after that I will need CVGLEMINATE. That's the function that I need, and for that the rest of the graph will be the same, and the rest of the code will be the same. I will simply copy that one here, the one we already done here. So that will be similar unless we do parallel computing. You can also add parallel 2 equals something, otherwise it will still be the same. So alpha will be the same, our variables. I'm not doing TF-IDF version of the data, so I will turn this off, and instead and then binomial. Well, we can also do parallel computing because we are doing cross validation, so that can be all the folders, they can be run in parallel. So there seems to be some readability. I want to make it more readable, so let me do it this way. And then also here too, actually, yeah. Now I can do for the other one. I can simply also copy this and then change few things. Otherwise, everything will stay the same. So let me call this one TF-IDF. And then here I will simply call the TF-IDF version of the data. Now let me calculate time for both. Actually, I can simply call this. I don't want to type things. I'm sometimes lazy, so I will simply copy and paste here. So let me just copy this one and then instead text this. This is the time. Actually, here I will simply I want to calculate how long this model takes. And then after that, I will simply write system time minus the old time minus the current time. Then with that, I will be able to do a cross-validation. Mind you, here you use a function, you use a CFSGLEMINATE, otherwise everything is the same, and you can simply call parallel equals true. This will may facilitate depending on how powerful your PC is. Otherwise, everything will be the same. The whole purpose of CVGLEMINATE is just to do tenfold cross-validation. Now let me run this and pause the video and come back in a minute. Now you see everything is done. It took about 11.5 seconds. It's super quick, and the next thing is to visualize this cross-validation. And we want to see, because we are doing this cross-validation, we want to see the deviance. The deviance is like, if you do logistic regression, if you do multiple linear regression or ordinary least square regression, then your error is sum of square error. But if you do logistic regression, your error is deviance. And then for this, we also have deviance. So that's the value that we want to visualize. So for that, what you do is simply we use a plot function, and then after that we simply call our reach CV, reach cross-validated version of our model, and then after that we simply give it a title, just to reach, and we can use that again new line, so that the graph should not be touching our value, so there should be space. And this is how our cross-validated version of our linear regression model works, because we have many models. So you see we have all of these errors. These are the deviance, and the model with the minimum, the value of deviance with the minimum error is our best model. So there are two values here. One is lambda mean. This is called the model at lambda mean, and this one is called the model at lambda 1 standard error. So usually we use this value for prediction. This is our best model. In some cases you may have like all this somewhere it may start from high and then it goes down and then it may go up like that. But in our case, the minimum, the deviance, like the minimum deviance value is where our this one is, so 1 point something. So this is where our best model is. So this is the model that we want to use for prediction, for predicting the unseen data. We're not going to use somewhere here or here or here. Then if you use somewhere here, then your prediction will be not much accurate. So, but to have to use the better model, so you need to use the best model, and for that we need to use the model for lambda mean. So we do the same plotting for the reach TF-IDF. So for that what we can use is we use reach CV and then TF-IDF. Simply change this. And then it also change this one, TF-IDF, because I'm using the TF-IDF version of the data, and I want to visualize the TF-IDF model, and for that I can simply run it. But again, at the same time, I want to put them side by side. For that I need this par MFO 1,2, because I want to plot them side by side. So I can simply call this here and run it. Now let me run this, and now this is how it looks like. In both cases, our model is the best model is at the very early phase of our lambda. So this will be now best model in both cases. And then let me see, if you want to see again, we can see summary of reach TF-IDF, actually summary of reach CV actually. Reach, my Jupyter notebook is reach. Okay, let me see reach CV. Okay, now this is how so it gives you the cross validation and the cross validation standard deviation, and all of them have all these values, and you have, of course, we have 100 lambda values provided by the g-eliminate function, and that's all. So if we want, you can see where my best model is. For that, what we need is we need this lambda and then the minimum lambda. So that's where our best model. So this will be our best model. So let me see, and this is where the lambda value is, but this shows 3 point something, so that's the best value for lambda. But again, we need to pass it with the log because it's log lambda, because it's logistic regression. So regression is the extension of logistic regression, so we pass it with a log. So that will be our best lambda, again 1.09 something. But let's see if we make it TF-IDF and see where that value is. So there is some error here, and so it's exactly the same actually. So it will be, it's exactly the same. So now I want to plot this one, and I want to combine these plots, and so we will see because this is a coefficient, and we will see, we will plot them. We will plot one standard error lambda and one lambda mean and lambda one standard error, and we will visualize it in this plot. For that, what we need is we need the upline function from the plot that we already did. So we simply call actually the previous plot, the one we did here for the two plots. So we simply call this, copy this, and paste it here, and then change a few things here. So let me add a few lines. So for that upline, we need uplines. This upline, for model plotting. So you use upline, and we want to use the vertical line. And then for the vertical line, what we need is a logarithm of which the model that we have, which cross-validated version of our model, and then lambda dot mean. That's what we want to use. And then let me color it. Maybe if we want, you can color it. Let me color it red. That's where my, and the line type, you can also define line type. Let's make it dash it, for example. And then talk to that. After that, what we want to add is we want to add the other one, the one standard error. The one standard error is, again, you simply change this one, otherwise everything will be the same. And we can change this color, or maybe let me make it blue. And maybe I can also turn this dashed line off, and we will see. Now we have for the for the non-TF-IDF version of our model, we have everything, but for the other one we don't have. So I will simply copy this and then paste it here. Now I will change simple things. The first thing I need to change is I want to use the TF-IDF version of the data, and then again I want to use the TF-IDF version of the data with lambda. I mean the TF-IDF version of the model, and then lambda one standard error, of course. And the color will stay the same, blue, the same to mine. So now this will plot the two models side by side, and it will plot these values in the previous model here. So let me run this, and it might take a little bit of time, maybe a few seconds, and then we will see. Yeah, see it. Well, I seems to have an error, so I must have made an error somewhere. So it's telling me a log reach TF-IDF lambda mean linear numeric argument. Oh yeah, okay. This is where I made the mistake. So this should be not reach TF-IDF. So instead, because we are doing several models in the cross-validation model, the cross-validated model, we have so many models. So for that, I need to feed the cross-validated version of my model, not the reach TF-IDF. Instead, I will need to give it a cross-validated version of my model. So let me copy this again and put it here. Now the graph should not have any problem. There you go. So we have our model, or regression, and we see that all of the coefficients, I mean all of the values, like we have 11,136 variables, and in both cases, in both of our models, all of them are retained until the end of our tuning, but the best model is somewhere at the beginning in a sense, where the lambda value is, the logarithm of lambda value is around 1.09, in both cases 1.09. So the prediction will not be really very far away from each other, because they are more or less the same model, but the difference will be in the way the TF-IDF version and the simple frequency version of our test dataset is coded. Otherwise, the prediction will not be, at least the models are nearly similar, because we have the same data. It's only one is standardized, this TF-IDF version of the data, and the other one is not scaled or standardized. So now this is our model. We already have our model. So the next thing in our agenda is I want to plot the very important, like variable importance or variable influence. So for that, I said we need. I have already said that we need a VIP package. We have already loaded VIP. What we need is a VIP function, and we just use VIP, and then we pass our model. Let's say what we pass is a cross-validated version of our model. So let me simply give. Actually, what we need is the CD. Okay, let me just try this, and then number of features. Let me just define 20, and then see how the variables is. We just want to visualize only 20 variables, and then after that we need to define the drone function, just like drone point, just like a ggplot2, and we use drone point, and we call it drone point. Okay, now we want to run the model and see what are the variables that we have. So these are the like the most powerful words that we have that are very important for the model. So these are like yeah, I don't know, somehow this doesn't really make much sense, but let me again see TF-IDF version of the data and then see how our model. So this is they are more or less the same. Yeah, so at least in the TF-IDF version of our data, it's telling us some of the really the most powerful, like important variables: syndrome, acute respiratory, COVID-19, and the like. And this is the most important variable in this model. In the TF-IDF version of our model, this is this variable called syndrome. Otherwise, yeah, here are the 20 most important variables. The importance is calculated based on information gain score, information gain value. If you don't know information gain value about, then it's better to read about it. Otherwise, I will pass to the next. But I think I forgot something. Because we are doing cross validation, it's always advisable to save seed. Otherwise, your results will not be reproducible. So if you are doing cross validation, or if your modeling has included some sort of sampling, then you always please don't forget to save seed. Yeah. So I will rerun everything and be back. I will pause it and be back with in a minute. So I have already rerun it. So let me actually again plot the variable importance side by side, and maybe I can use again that function MFO, and then I will use this C concatenated by 1 to 2, so that everything will be visualized in one row. And let me plot this TF-IDF version of the data, and now let me rerun it. But it doesn't seem to be, because the space is not enough, so it's putting one after the other, so it doesn't seem to work with this one. Anyway, the first version of our model without the TF-IDF version of our data, it's telling us these are the most important variables, like personals, and variables like anthroplasty and proofing, and the like, and then it goes down. But the second one, the TF-IDF version of our data, is telling our model actually, which uses a TF-IDF version of the data, is telling us syndrome, acute respiratory. These are really the most common words in these COVID publications. So that's why still coming to be most influential variables. Now we have already the model, we have the variable importance. The next thing is evaluation of the model. So we will evaluate the model and we will see how it works. So for that, what we need is the predict function, and then and then we will be passing our model in the data set, and everything will be ready. So prod reach, let me call it prod reach. I want to predict my model. The unknown test data set. So I will use predict function, and then the first thing I need to do is reach CB. How many models? So I need to reach CB. But if you know and then the next one is actually so once you predict and then you model and then the new data. So let me give it new X. Actually, it's called new X. Actually, I'm not sure. This predict function is from JEliminate. But there are also predict function within Caret or any other model. But this predict is I think provided by the JEliminate function. So for predict, and then you give it the model, and then you give the new X. For the new X, this is the unknown data set that we want to feed our model so that it will predict. Then after that, what you need is S function, this S argument, and that S argument is the argument that you tell which particular model are you interested in using for prediction. Because we have cross-validated model, we have several models from lambda 1 to 100. So we want to see, we want to use only the lambda mean for prediction. You can also try lambda 1 standard error, but this is where the model with the minimum deviance is. So it's more, it makes sense to use this model for prediction instead of the one standard error. I have seen some people using the 1 standard error, but that's it makes sense to use the lambda mean, because that's the minimum where the minimum deviance or the minimum error is. And when we will give it a type, if you want to type the class or probabilities, we'll use we want to predict the class. We don't want to see the probabilities, but you can also see the probabilities. So for this, we're not going to show the probabilities. I'm only interested in knowing the class. So this class, it will simply change the probabilities to like hardline classes like COVID or SARS, depending on your category of your data, your outcome variable. Now let me call it TF-IDF, and then I will give it again TF-IDF version of my model. And then from that again, I will give it the TF-IDF version of the data and see how this works. Otherwise, the rest of the argument will stay the same. I will simply change this, and here the model type. This is ARIA. Let me change this one, and then give the TF-IDF version of my dataset and run this. So it's quick. It's already completed. So the next thing I want to do is I want to see my confusion matrix. Let me call it reach conf mat. It's already there. So reach conf mat, and then let me give it a confusion matrix. Let me call this confusion matrix function from Caret, and then within confusion matrix, what I do is I need to call table function, and then I want to actually let me show you this way instead. Let me put this one. Let me put it down here, so then it will be easier. So let me just stop this one, and then simply again this one again. Then tabulate. Now I want to tabulate first the table, or of prod reach. So I already have prod reach versus test input. So if I tabulate, you will have a 2 by 2 table of our data. So now using this function, I will simply pass the confusion matrix, and then confusion matrix, I will simply pass it. Now we will see confusion matrix. And something is wrong, so I didn't pass a bracket here. Yeah, now it should be, but I just need to define one more thing, and I give it this everything. So everything within that confusion matrix will be printed out. Now I will see the prediction, but let me give it that name. Now the name I already assigned, confmat, which confmat, so then I can use this later if I want. And then after that I can simply print. Yeah, there you go, how this our prediction looks like. So we have an accuracy of 86.7 and sensitivity of about 85%, and the specificity is 88%. Again, the precision is another important figure. They all look very good. But let me make it again with TF-IDF. So for that, the TF-IDF version of the model and the TF-IDF version, I'll simply, so let me simply call this TF-IDF, and again, let me copy paste this, and then change two things. I already have prod reach TF-IDF, so I simply call this, and then for this one, the rest will be the same. I don't change anything because I don't have the dependent variable is not changed into TF-IDF or something. It's the same. We didn't process it. Now we can compare. Which of the model performed better, the TF-IDF version of the data, or the TF-IDF version of our model, or the simple frequency model without weighting or standardizing or scaling using TF-IDF method. So let me run this, and now you can see the first one was about the accuracy of 85%, no, about 86.7. But again, it's also the same, but there might be something different. Let's see the 2 by 2 table. So 129.50. So it's correct here and here, but it's making errors on this part of the. Let me see again. So this one making good job here. That one was 129, and then this one is also making good job here. Let's see. So that means this is 84.9. This is 88.65, and this one is making good job in terms of excluding COVID cases, like the negative cases, which is 89.36. That's why it's performing good job. It's performing good here. So that's why the previous one was 16 here. Yeah. Now that's how the detailed confusion. If you print the detailed confusion matrix looks like. Anyways, this model seems again to have worked very well, but it can't be close to what we have seen before for all of these models. If you remember, conformal linear TF-IDF, I think the radial was the best, but I don't remember. So anyway, this one was 94%, which is 95% sensitivity and accuracy of 94% again. And let me just check it again, which is the one we have already seen. Again, this is within 80%, and let me check again linear, and again 93%. 93%. This is again a very good one. And let me see. I think sigmoid was the best. Sigmoid SVM 92, 93, 90. I'm more interested in seeing the specificity, accuracy, and those models. So let me again see the sigmoid that we have already had. I think SVM sigmoid. How many models do we have? So it seems I don't have sigmoid SVM. Okay, I didn't print that object. Anyway, we can also scroll up, or if you want, we can simply sigmoid. Yeah, you can see how this model. So we have already tuned sigmoid SVM, and we see how the sigmoid model actually worked in our previous tutorial. So let's see. It's still we are. This is linear. Okay. So it's SVM sigmoid, and then after that, SVM tuned. What did I call it? Okay, well, I need to pause the video and search it actually. Oh, yeah, so I found it. So this is our previous model. I have already loaded all the objects, so we can print it out and see whether that was actually our best model. So let me print it again, conformal sigmoid, and then yeah, so this was our best model. So this is about 95% accuracy, and then a sensitivity of 98%, which is remarkably excellent. And let's see again. So again, this is not as accurate as conformal sigmoid, as sigmoid kernel SVM. So far the best. There is nothing we have seen that beats as sigmoid SVM, even though it takes a bit of training time. Yeah, but still we have seen the best performance from sigmoid SVM for text data. That's all for regularized rich regression model. So next time we'll talk about lasso regression model. Lasso is actually one of the most interpretable models. So we'll see in the future about lasso regression, and then after that we will also see elastic nets. But otherwise, that's all for rich regression today. I hope you have enjoyed this video, and thank you for watching this, and I hope you will continue subscribing to this content. Thank you very much.